In the previous videotape, we discussed the vital role that protection plays in the power system. We also looked at the basic factors and requirements which affect protection schemes, the need for zone protection, backup, and so on. Now, we'll turn to the building blocks of protection. In this videotape, we're going to look at the most common types of protective relays which form the prime element in any protection scheme. In future tapes, we'll see how different relays are combined to form a coordinated system. Most of these relays are available in both electromechanical or solid-state form. Either way, although the hardware is different, the operating features, characteristics, and adjustments are similar. One of the most sensitive methods of protection is provided by the differential relay device number 87. Indeed, this is usually the first choice for protection of such items as generators, transformers, buses, and large motors. This is a typical example of an electromechanical differential relay. Its main components are the differential unit, restraining coils, trip contacts, harmonic restraint unit, instantaneous unit, and targets. We'll see what these items are for in a moment. But first, let us examine the simple differential principle. Here, we wish to protect against a fault occurring on the bus. Under normal operating conditions, that is, with no fault on the bus, the current entering the bus from feeder F1 must be the same magnitude as the current leaving along feeder F2. Let's suppose that this current is 1,000 amps. Let's see what will happen if a high resistance fault occurs on the bus, resulting in a passage of, say, 200 amps to ground. Now we have 1,200 amps entering the bus and 1,000 leaving. By locating CTs in the feeders, we can compare these currents and connect the CT's secondaries to a relay. If we assume that the CT ratio in each case is 2,000 to 5, it is apparent that we have 2.5 amps circulating in the secondary of the outgoing CT and 3 amps flowing in the incoming CT. Note that it is the location and connections of the CTs which provide the relay its differential operating current. The difference, 0.5 amps, will flow through the relay operating coil and so close the trip contacts, providing that the relay is set to trip at that value. Typically, differential relays are set to trip for a pickup current from as low as 0.14 amps and up to 3 amps. The tripping circuit would then open all breakers connected to the bus, in this case on feeders F1 and F2. So you can see that the relay is quite sensitive and can be made to trip for even a modest out-of-balance current. Obviously, where there is no fault on the bus, the currents flowing in each CT will be identical. In this situation, zero current will flow through the differential coil and no tripping will take place. Now, let's take a look at the case where the bus suffers a serious failure and there is a direct short circuit to ground. In this case, the current flowing into the fault along F1 will be quite high, say 5,000 amps. And what about feeder F2? Well, depending upon the system configuration, the flow of current in F2 may fall close to zero, or it may well reverse and also feed into the fault. Obviously, in this situation, we will have a very high value of differential, as the secondary currents will now be additive in passing through the differential relay operating coil. The relay will close its operating contacts and trip the breakers. How will this differential relay act in the case of a fault out here on F2, that is, a through fault? Well, the current in each CT is now balanced, even though it is higher than normal, so the relay will not trip. Is this good? Well, the answer is yes. we want the relay to be selective and operate only for an internal fault. This allows the fault on F2 to be cleared by other relays, opening breaker F2 but leaving the bus energized. Now let's look at the differential relay as applied to protect a transformer. This works on the same principle, but of course the CT ratios on either side of the transformer have to be chosen so as to give the same secondary current. That is, it must compensate for the current transformation in the transformer itself. In this example, we have a 10-to-1 step-down transformer. That is, from 230 kV down to 23 kV. And for simplicity, we are dealing with the single line diagram. Let's assume that normal load current on the secondary side is 2,000 amps. Then the chosen CT ratio will probably be 4,000 to 5, giving us 2.5 amps in the secondary circuit. For this condition, the high voltage primary current will be 200 amps, ignoring transformer losses. And in this case, the chosen CT ratio will be 400 to 5 to give equal secondary current 2.5 amps. However, in practice, there are transformer losses and also losses associated with the CT secondary leads, which may differ considerably in length due to station layout. Moreover, it is almost impossible to produce current transformers with absolutely identical characteristics, especially when they have such widely different ratios. The result of this is that even when operating conditions are normal, that is, there is no internal fault in the transformer, there will still be a slight imbalance between the secondary currents flowing in the CT circuits. This means that a small current, let's call this the error current, will flow through the differential relay operating coil. In an attempt to reduce this error current as far as possible, differential relays are typically provided with a number of taps to help balance the CTs. But even with this, a small error current usually does exist. Now, under normal operating conditions, this will probably be below the pickup value of the relay, and so will not close the tripping contacts. However, things may not be so comfortable where we have an external fault which causes a high current to flow through the transformer. In this case, the CTs will be measuring a balanced condition, but the error will be magnified and may cause the relay to operate. Similarly, transformer tap changers introduce problems with CT ratios. In order to avoid these problems, restraint coils are normally fitted to the relay. Typically, the restraint coils are wound on the same core as the operating coil, but in the opposite direction. A separate restraint coil is connected into each secondary CT circuit. So how does this work? Well, let's suppose that due to inaccuracies in the CTs, we have, say, 2.6 amps flowing in this secondary and 2.3 amps in this one. As a result, there is an error current of 0.3 amps flowing through the relay operating coil. Will this be sufficient to operate the tripping contacts? Well, yes, if the relay pickup is set low enough. But we do not want the relay to trip under these conditions. And that's why we have restraint coils, which are both trying to hold the tripping contacts open. The value of current in the two restraint coils is respectively 2.6 amps and 2.3 amps. Depending upon the relay's setting, this restraint should be sufficient to hold open the tripping contacts against the closing torque of the operating coil. The actual closing force on the tripping contacts depends upon the ratio of the error current to the restraint current. In our example, that is 0.3 amps error current divided by 2.45 amps, the average secondary current, equals 12.2%. In order for the relay to operate, the current in the differential operating coil must be greater than a preset percentage of the current in the restraint coils. If this percentage differential, called slope, is set to, say, 15%, then the relay will not operate. In fact, we would need an error current of over 0.367 amps to make the relay operate. Many differential relays are provided with taps that allow us to set the percentage differential or slope from 10 to 50%. This chart shows a family of curves. This indicates for each case the minimum current required in the operating coil to trip compared to the magnitude of current in the restraint coils. For example, to trip at 25% restraint, it will require a current of 1.5 amps through the differential operating coil if the average secondary current, that is, restraint current, is 6 amps. In other relays, the percentage differential is not variable and must be specified upon purchase. There is yet another design that provides a variable restraint. At low current flow, this provides very minor restraint, perhaps equal to 10%. But as the flow-through current increases, the restraint also increases to over 50%. Remember, the objective of restraint coils is to prevent the relay from operating inadvertently in the case of an external fault, which causes a heavy flow of through current. Where the fault is internal, there would normally be a great differential between the two CTs, and ample current would flow through the operating coil to overcome the restraint and trip the relay. Where differential relays are used to protect large power transformers, it is usual to fit yet another restraint unit into the scheme. And this is harmonic restraint. This unit acts to prevent inadvertent tripping of the differential relay due to transformer inrush current. What do we mean by this? Well, as you know, when a transformer is being energized, normally on the primary side first, a very high magnitude of current is drawn to magnetize the core. This is the exciting current. This inrush current may only last for a few cycles, but it could easily provide a false signal to the differential operating coil. After all, there is no current at all in the secondary of the transformer. There are several ways to prevent inadvertent tripping. In one method, the harmonic restraint unit opens a contact which is connected in series with the differential tripping contact shown in this simplified diagram of the tripping circuit. This normally closed contact is held open until the inrush current has subsided, and so makes the tripping circuit inoperable during this period. But how does it know that the high current is inrush and not an internal fault? This is the schematic for the harmonic unit. It is actually a tuned circuit made up of capacitors and reactors designed to detect second harmonic current. What do we mean by second harmonic? Well, in the initial charging of the transformer, a very high magnetizing current is required, which distorts the normal 60 hertz current sine wave. When analyzed, we find most magnetizing current is second harmonic component, that is, a current at twice normal 60 hertz frequency. There are actually two tuned circuits. The operating coil circuit presents a low impedance to 60 hertz current and a high impedance to 120 hertz current. The restraint coil circuit is just the opposite, presenting a low impedance path to second harmonic current and high impedance to 60 hertz current. When energized, the restraining coil opens the permissive contact in the tripping circuit. After the inrush current has subsided, the second harmonic will disappear. The permissive contact will close, and the differential relay will operate normally. Now, there are several different ways of achieving the same result depending upon the specific relay design, but the objective is the same. If a heavy internal fault does exist during energization, the unit is normally protected by an additional relay, just to make sure that it does trip. This is a built-in instantaneous relay that is fed directly from the CTs without restraint. Its operating contacts are wired in parallel with those of the restrained differential unit. So as to avoid inadvertent tripping, it is set to operate for very high levels of internal fault, say 10 to 15 times normal full load current. When the differential relay does operate, specific targets will indicate instantaneous or differential trip and which phase has faulted. In future videotapes, we'll be seeing many detailed applications of the differential relay. But at this point, it's important that you fix the principle of differential protection in your mind. For now, let's take a break and please switch off the tape and go through this material in your workbook. Although the differential relay gives excellent protection for generators, transformers, and buses, it is not really suitable for feeder and transmission line protection. This is because the CTs would need to be located at either end of the line and the secondary leads conducted over a relatively long distance. This is expensive, and more important, the impedance of the secondary conductors could give rise to serious inaccuracies. As we shall see in future tapes, the differential principle is used for special applications. But a more common form of feeder protection is overcurrent. For example, a fault out here on this feeder would give rise to an overcurrent in the line. An overcurrent relay connected close to the breaker would detect this and could be set to open the breaker. The standard device number for an instantaneous overcurrent relay is number 50. Here is a typical instantaneous overcurrent relay of the clapper type. Its principle of operation is extremely simple. The CT measures the current in the primary line, and the CT secondary passes this current through the coil of the electromagnet. The resulting magnetic force pulls the hinged armature, that is, the clapper, against a restraining spring. If the current input to the relay is above the preset pickup level, then the relay contacts will close and so energize the tripping circuit. The pickup level can be adjusted by selecting taps on the coil and also by adjusting spring tension. Here's another type of instantaneous overcurrent relay, the plunger type. In this case, the electromagnet pulls the plunger up against the force of gravity. Again, the pickup level can be preset by adjusting taps and also by adjusting the position of the core. When current exceeds the pickup level, the instantaneous relay will operate within about 50 milliseconds, that's about 3 cycles, and energize the tripping circuit to open its associated breakers. This instantaneous action can prove to be a problem at times. For example, if a large consumer load is started, say a large motor, it will pull a considerable surge of current for a few seconds. This may well be high enough to trip the instantaneous overcurrent relay and so isolate the whole feeder, including all other customers. To avoid this, the operating pickup must be set to a very high level. And certainly this would be adequate for protection. Adequate for protection of severe faults on the line. But how can we protect against low-level faults? This is achieved by use of the time overcurrent relay, device number 51. This is a typical electromechanical time overcurrent relay. Its main components are the electromagnet, the operating coil, the rotating disc, tripping contacts, and time dial. Secondary current from the CT is passed through the operating coil, which is wound around the central leg of the electromagnet. It sets up this magnetic circuit. The flux passes through the non-magnetic disc and then returns through the disc again to the outer legs of the electromagnet. In this condition, the disc will not rotate, as these two fluxes are in phase. However, by placing a shorted coil called a shading coil around one outer leg, a phase displacement occurs. Flux in this leg will now lag the other, and this causes the disc to rotate. The disc is normally held stationary by a retaining spring. Only when there is sufficient current passing through the operating coil will the disc start to move. That is the pickup level. Remember, the magnitude of current in the operating coil is proportional to the primary current along the feeder, which we are protecting. So the greater the primary current, the greater will be the operating current, the greater the flux, and in turn, the faster the disc will rotate. You can see here, as the disc rotates, it carries with it the relay operating contact, and this eventually is brought up against the fixed contact, so closing the tripping circuit. This is the well-known inverse time characteristic as shown by this family of curves. The time for contact closure is shown on the vertical axis, plotted for different values of relay operating current. The higher the level of fault current, the quicker the operation of the relay. Moreover, for any particular current value, we can adjust the operating time by adjusting the time dial here. What this actually does is to change the distance that the moving contact must travel. As the family of curves indicates, a time dial setting of 0.5 indicates the shortest operating time, while a number 10 setting will give us the longest operating time. When reading these curves, please remember that the value of current along the base is expressed relative to pickup current, that is, as a multiple of tap setting. For example, supposing that the coil tap is set at 2 amps and the relay current is actually 10 amps, that is, 5 times the tap setting. Now, if the time dial is set at 6, we look at this particular curve and find that the relay will operate in 1.55 seconds. If the time dial is set lower, it will operate much faster. This particular characteristic curve is known as very inverse. When specifying a relay, it is necessary to indicate whether an inverse, very inverse, or extremely inverse characteristic is required. We can see the difference on this chart. The extremely inverse type shows the steepest curve. That means it has the slowest response for relatively low current levels, but in contrast, it has extremely fast action for higher current. The characteristic curve can be slightly modified according to the position of this damping magnet. But this magnet is set in the factory and should not be adjusted during normal maintenance and testing. The type of characteristic is sometimes indicated on the nameplate of the overcurrent relay. Check this out next time you're in a substation and perhaps speculate why specific characteristics are chosen. This schematic shows a typical tripping circuit. This is the trip coil which will operate the breaker. Sometimes this is operated through an auxiliary relay so as to reduce the current which must pass through the relay contacts. A seal-in circuit is normally connected across the relay contacts so as to protect against contact bounce or inadequate closure. When the time delay contacts touch even momentarily, the seal-in relay picks up and the circuit now remains securely closed through the seal-in contacts. Only when the breaker opens does this auxiliary contact open, thus interrupting the tripping circuit and de-energizing the seal-in relay. Often the time overcurrent relay includes an instantaneous element built into the same casing. As they must respond to the same CT secondary current, the operating coils are connected in series. The instantaneous relay tripping contacts are independent, wired in parallel with the time overcurrent tripping contacts. Thus, in this typical trip circuit, either contact can complete the circuit and trip the breaker. The instantaneous relay will be set at a relatively high value and will only operate in case of an extremely high-level fault. When the relay does operate, a target will drop for either the instantaneous element or the time overcurrent element. This will inform the operator that the relay has operated and help him analyze his system problems. Overcurrent relays are widely used throughout the power system, not only for feeder protection, but also for motors in industrial applications and for backup protection in other areas. When applying time overcurrent relays of the electromechanical type, 2 points that must be considered are over travel and reset time. Once the disk is rotating under fault conditions, inertia will cause the disk to continue slight movement, even if the current falls below pickup value. This over travel could cause inadvertent tripping. Moreover, the disk will not reset immediately. In some relays, not until the operating current falls below about 60 or 70% of pickup. If a repetitive fault occurs, the disk may not have time to reset completely, and each repetition may cause the disk to creep forward, and so after 2 or 3 repetitions, ultimately trip. These limitations must be borne in mind when calculating relay settings. Generally, overcurrent relays are constructed as single-phase units, and several relays are required to provide 3-phase and ground protection. The same type of relay with similar characteristics but different wiring is also used for over and under voltage protection. Now at this point, let's take a break, and then we'll come back and look at directional elements, which are often used in conjunction with overcurrent relays. For now, switch off the tape and thoroughly review this material in your workbook. When the overcurrent relay senses fault current, it will operate irrespective of the direction of the current flow. Quite often, we would like the relay to operate for current flow in one direction only. Let me show you why. This example shows the high-voltage bus in a distribution substation. It is fed from sub-transmission lines, which are part of a continuous loop. In this arrangement, current may flow in or out of either sub-transmission line, depending upon conditions or system configuration in other parts of the loop. Now, suppose a fault occurs on line A. Fault current will flow from line B through the bus to feed the fault on line A, in addition to the load on the bus. The overcurrent relay on line A will sense the overcurrent situation and begin to operate according to its inverse time characteristic. But the current in line B has also increased to feed the fault. Therefore, its own overcurrent relay will also sense the high-level current and commence the tripping process. In fact, line B is also feeding the distribution load and therefore passes greater current than A. If the B relay trips out line B, the substation is left without any power supply at all. We can avoid this by using directional overcurrent relays, device number 67. Now, with a line A fault, the directional element blocks the overcurrent relay on line B from tripping when current flow is into the bus, but it will allow operation of overcurrent relay A to trip when current flow is out of the bus. For both of these lines, the correct tripping direction is when current flow is out of the bus into the line. In the case of a bus fault, current will flow into the bus from both feeders. Then both overcurrent relays will be blocked from operation by their respective directional relays. The fault would be cleared by other protection relays tripping out the same breakers, a clear case of zone overlap. The directional element controls tripping by superimposing its operation on that of the overcurrent relay. You will remember that the time overcurrent relay is fitted with a shorted shading coil on one leg of the electromagnet. This is to provide the driving force. The shorting circuit is fitted with a contact, which is operated by the directional element. When current flow is in the tripping direction, this contact remains closed and the overcurrent relay can operate. However, if current flow reverses, then the directional element opens the contact, so preventing operation of the time overcurrent relay. Similarly, the directional element also operates a contact in the instantaneous relay tripping circuit to allow tripping only when current flow is in the designated tripping direction. There are several different types of directional relay, but they all work on the principle of comparing the direction of current flow with some fixed reference, which may be voltage or current. To be more precise, it is usual to compare the phase angle of the current in relation to that of the reference. The important point is that the polarity of the reference quantity, be it voltage or current, must not change even under different fault conditions. For example, if current is used as the polarizing quantity, it can be obtained from a CT located in the grounded neutral of a Y-connected transformer. In this simple arrangement, the directional element receives reference voltage from the VT on the bus. Current is measured by the CT in the protected line. In normal operation, the phase angle of the current may be up to, say, 20 degrees lag. But if the direction of current flow reverses, then the phase angle will change by 180 degrees. This very large difference is easy for the relay to detect and activate the directional element. One common type of directional relay is the induction cylinder type shown here. The aluminum or copper cylinder takes up a stationary position depending upon the fluxes developed in the electromagnet. One of the coils is receiving input from the reference voltage or current, while the other is receiving input from the CT of the protected circuit. When current flow is in the selected non-tripping direction, the two fluxes set up the cylinder so that its contacts block operation. Now, if the flow of primary current reverses, then the aluminum cylinder will immediately take up a new position. Its contacts will now allow rotation of the time overcurrent disk, and the relay can operate. It will also close the permissive contact in the instantaneous relay tripping circuit. This constitutes directional control of the overcurrent relay. Of course, there are various other methods for achieving the same result, but the concept is the same. When current flows in the tripping direction, the directional element allows the overcurrent relay to operate. When current flows in the opposite direction, that is the non-tripping direction, then the directional relay will prevent operation of the overcurrent relays, both time overcurrent and instantaneous. Obviously, the actual tripping and blocking directions can be reversed by simply changing the polarity of the connections. In this particular relay that we've been looking at, the instantaneous overcurrent element is of a different type to that discussed in the previous segment. It works on the induction cup principle and is in fact quite similar to the directional unit. The secondary current from the CT is passed through these electromagnetic windings. A capacitor is wired into the circuit of one of the coils so as to provide a phase difference between the two fluxes and in turn produce turning motion on the cylinder. The spring restrains movement of the cylinder. However, as soon as the current flowing through the coils increases above the set pickup value, then the induction cylinder will rotate and close its trip contacts. In this unit, only a few millimeters of rotation are required so that the tripping times are extremely short, about 20 milliseconds. Clearly, the directional element plays a very important part in coordination and selectivity of the system protection schemes. We'll be talking a lot more about application of these relays in future tapes. For now, time for a break. Please switch off the tape and review this material in your workbook. In an earlier segment, we saw how the overcurrent relay is commonly used for protection of distribution feeders. However, on high-voltage transmission lines, the preferred method of protection is usually through the application of distance relays, or impedance relays, as they are often called. Why? Well, distance relays are faster, more selective, as selectivity is obtained on the basis of voltage changes as well as current. Easier to coordinate because they are not affected as much by short-circuit magnitude and hence changes in generating capacity and system configuration. The device number for the distance relay is number 21. The earlier types of distance relays worked on the balanced beam principle like this, and certainly this is the easiest way for us to study the concept. The beam is pivoted like a seesaw with voltage and current coils at opposing ends. The voltage coil is fed from the voltage transformer on the line, or more usually on the bus feeding the line, while the current coil is fed from the current transformer on the protected line. Under normal operating conditions, the voltage coil's attractive force is far stronger than that of the current coil. Hence, the balance beam stays in this position. However, if a fault occurs on the line, then the magnitude of current increases greatly, with the result that the current coil now produces much greater attractive force and will overcome the restraint of the voltage coil. The balance beam seesaws in the opposite direction and closes the contacts in the tripping circuit, so tripping the line circuit breaker. The actual point of tripping could be set by adjusting the position of the center pivot, or more simply, by adjusting taps on the voltage and current coils to increase or decrease the number of turns. Either way, the actual point of tripping depends upon the comparison. That is the ratio of voltage to current, V over I. The relay is in fact measuring the impedance of the circuit being protected, including the load impedance. However, if we have a fault on the line, say a direct phase-to-phase fault, then the circuit impedance to the fault is only that of the conductors themselves, and as we know, this is a relatively small value. Indeed, this is the very reason that the current increases to such a high magnitude. So the relay is set to operate when the measured impedance falls below a specific value. If we know the impedance per mile of the line conductors, we can set the impedance relay to trip for faults within any particular distance from the relay. For example, let's say this line is 125 miles long, and the total impedance is, say, 100 ohms. At the halfway point, the impedance will be 50 ohms, at three-quarter length, 75 ohms, and so on. The relay will be installed at this substation close to the breaker, but it can be adjusted to reach out as far along the line as we wish. Typically, it will be set to protect up to 90% of the length of the line, that is, for an impedance of 90 ohms in this example. Why? Well, relays have a 10% error margin, and we don't want the relay to overreach. The relay is using secondary values from the CTs and VTs, so it really measures secondary impedance. The relay continuously compares voltage and current, and if the primary impedance falls below 90 ohms, it will trip its associated breaker. However, if a fault occurs beyond this line, the impedance will be higher than 90 ohms, and the relay will not trip. So the relay is giving us the desired selectivity. Usually a second element is installed to protect the remainder of the line and reach out into the second zone. A third element may be added to reach even further and so provide backup protection for the first and second zones. In each case, a timer is added so as to delay operation of the second and third elements in order to allow the primary protection to operate in those zones. It is important to note that we are talking about the impedance that is measured by the relay, not the resistance. Obviously, this is because the conductors contain both resistance and reactance. Typically, the conductors in this 125-mile-long transmission line will contain a resistance of, say, 50 ohms and reactance of 86.6 ohms. Let's plot this on an impedance diagram. Resistance is shown along the horizontal reference vector, and inductive reactance is shown on the vertical axis. Capacitive reactance, if present, would be shown on the negative vertical axis. In this example, we will assume that the quoted 86.6 ohms reactance has taken into account both inductive and capacitive reactance. Plotting resistance and reactance, we find that the total impedance comes to 100 ohms, and it is at an angle of 60 degrees from the reference vector. If we were to set our relay to protect, say, 90% of this line, then the operating point would be here, at 90 ohms. The relay would operate for any impedance along this line between 0 and 90. But that's not all. With the simple balanced beam type relay, it would operate for anywhere within this circle, where 90 ohms is the radius. The balanced beam does not take into account phase angle or direction of current flow. It will trip as long as the measured impedance falls below 90 ohms. In fact, it would trip for a fault upstream, that is, on the bus or on the line feeding the bus. Look, even though current through the CT is reversed, the relay still responds to high current in relation to voltage. That is, it sees a low impedance. On the circle diagram, this operating point would be out here in the third quadrant. To avoid this problem, directional relays, device number 32, are usually combined with balanced beam relays in order to restrict operation to faults downstream of the relay. So this first quadrant is the part of the circle diagram which interests us. We can add to the same diagram the operating circle for the second zone and another for the third zone protection that we mentioned. In each case, the relay element will pick up if impedance falls within its respective circle. For example, a fault out here in the second zone may cause impedance to fall to, say, 140 ohms, which is less than the second element set point of 160 ohms. The relay will operate, and after its timer has timed out, the breaker will trip. But we have not yet considered the impedance of the load. Where does this fit into the picture? Let's take an example. Here we have our same 132 kilovolt line feeding a 90 MVA load on the B bus. That is 76 kV line to neutral and 30 MVA per phase. This gives us a line current of almost 400 amps. Dividing current into voltage, we get 76,000 volts divided by 400 amps equals 190 ohms. This is the impedance of the load. Let's say the load is operating at a power factor of 0.9, that is about 25 degrees lagging. The load impedance can be shown off bus B on the circle diagram like this. But the relay measures the total impedance, that is the load plus line conductors. So we must add these values vectorially on our circle diagram. We see now that the measured impedance is well outside of the first zone of protection, but it is not far outside of the third zone. So the relay will not operate, and the condition appears to be satisfactory. But on large transmission systems, we often experience load swings. During such a surge, an increase in current could be seen by the relay as a decrease in load impedance, and it may well fall within the third zone of protection. If the surge remained for several seconds, it would cause tripping of the first breaker. Do not forget that our relay for first, second, and third zones is located on bus A. The same thing would happen, of course, if the total load was increased from, say, 90 to 160 MVA. In this case, the impedance may even fall below the setting of the third zone and cause tripping. It is important to remember that where the distance relay is concerned, some consideration must be given to the load characteristics as well as the impedance of the line. Because of these limitations, the balanced beam relay has been superseded by improved types of distance relay, and we'll be looking at these in the next segment. For now, it's time for a break. Please switch off the tape now and go through this material in your workbooks. The Mo relay is typical of the improved type of distance relay. Instead of the beam, this uses a cylinder moving within a magnetic field, similar to the directional overcurrent element. Coils are wound around the electromagnet, and these are fed from the CTs and VTs of the primary circuit. The circuitry is designed to give the relay specific characteristics, as shown by this circle diagram. The relay will operate if the measured impedance from the point of origin falls within this circle. The main feature of this relay is that maximum closing force of the relay occurs when the impedance is at a specific phase angle, usually about 60 degrees. This is similar to the phase angle of the line conductor impedance. The result of this characteristic is that as the impedance phase angle changes, let us say becomes smaller, then the unit will operate only for a lower impedance, that is, a higher level of current. This means that it is less susceptible to incorrect operation due to the load impedance, which can cause the relay's impedance to have a very low phase angle down here. Remember, this unit will only operate for faults within the circle. However, in some cases, we may actually want the relay to operate as a backup for close-in faults upstream. In this case, the characteristic can be offset like this, so that it will operate for very low impedance in the reverse direction. For example, a phase fault upstream but close to the bus would provide a very low impedance and probably fall within the circle here and so trip the breaker. For second zone protection, the second element can be offset like this. Again, because of the relatively narrow band, it is well outside of the load impedance. Phase to ground faults, especially on short lines, provide a particular problem for the distance relay. The arc often contains considerable resistance, so reducing the phase angle of the measured impedance. It also increases the magnitude of the impedance. Consequently, even if the fault is only halfway along the line, the measured impedance often falls outside the operating circle. A common method of getting around this problem is to install relays which measure reactance only. The operating characteristic is shown by this horizontal line. Reactance is measured on the vertical. During normal operation, the total reactance of the load and the transmission line will be above the operating set point. This will be 90% of 86.6 ohms or 78 ohms in our example. If a ground fault occurs halfway along the transmission line, the relay will detect the decrease in value of reactance to 43 ohms and operate the tripping contacts. It will not be affected by resistance in the arc. One problem is that the reactance relay is not directional, and so will operate for faults upstream of the protected zone. This problem is resolved by using the reactance relay in conjunction with a Mo element. The characteristic is shown on this diagram. There are two reactance elements, each protecting first and second zones. The circle diagram for the Mo element shows that it is set to protect the third zone. It includes an external timer to prevent early tripping. But additionally, the Mo element also contains a permissive contact in the operating circuit of the reactance relays. This restricts operation of the reactance relays to this area. The permissive contact will only close when the impedance falls within the circle. If the fault is upstream, the reactance relay will operate, but its tripping circuit will be incomplete because the Mo relay will not have operated and the permissive contacts remain open. Because of this, the Mo unit is often referred to as the starting unit, since it must operate before other units in the relay can trip out the circuit. Distance relays of the solid state type are designed with yet other variations in operating characteristics. Clearly, the impedance type of relay is quite complex and is well developed. It has many desirable characteristics for application on the transmission system, as we shall see in future videotapes. Now, the types that we have been discussing are the most common. If you want further details, you can always refer to our video program on test and calibration of specific relays. An important feature of the distance relay is the provision of zone protection, generally 3 zones. This allows us to provide backup. Generally speaking, the first element protects the primary zone as shown here by opening the first breaker, breaker A. The second element provides local backup in case the first element fails to operate. That is, it would trip breaker A after a short time delay. The second element also provides remote backup in the case of a fault on bus B or out on line 2. This would only operate and trip out breaker A in case the primary protection at bus B failed to operate. Similarly, Zone 3 protection is provided as remote backup for faults along the remainder of transmission line 2 and on into line 3. Also, for protection of line 1, a set of distance relays will be installed at bus B looking towards A. The first zone elements overlap, and a fault occurring within this zone would cause the instantaneous operation of both relays and the opening of both breakers. Now, for a fault in the last 10% of line 1, breaker B trips instantaneously, but we would have to wait for zone 2 clearing at A. Remember, remote backup will isolate a greater part of the system and perhaps cause outage to a greater number of customers. Also, there may be more damage and system shock. In this context, intertripping using various communication channels could be used. We'll discuss this in future tapes. Nowadays, more emphasis is being placed on local backup. Several types of protection are provided for each zone, and frequently a duplicate, so-called redundant installation of identical relays is provided. This would be fed by separate CTs and a separate source of DC tripping current. This in turn will be fed to separate tripping coils within the breakers. Usually in a fault condition, both of these protection circuits will operate in parallel at the same time. We will be looking in more detail at backup and the application and operation of distance relays in future tapes. In this videotape, we've tried to survey the main features of the most common types of protection relay. Of course, there are other types of relays, such as frequency relays, negative phase sequence relays, as well as many others which we have yet to discuss. But don't worry, we'll get to these in due course. Now that we have a good understanding of how relays work, we'll be looking at some of the basic technology of protection in the next tape, before moving on to study specific applications. For now, please switch off the videotape and very thoroughly go through this material in your workbook.